every night, countless billions of stars gaze down upon you in total silence. Scientists have established that our galaxy alone contains more planets than every grain of sand on every coastline on Earth. The numbers say the cosmos should be bursting with intelligent life. And yet, nothing. No signal, no arrival, no trace, just a silence so profound it approaches the impossible. Tonight, we cut through every credible theory researchers have put forward to explain that emptiness. From a galaxy-spanning extinction engine to civilizations cowering in fear, to the staggering prospect that we are the very first minds in all of existence to ask this question. If this thought haunts you at night, like and subscribe. Now, brace yourselves. We begin. The universe is roughly 13.8 billion years old. Across that incomprehensible span of time, stars ignited, worlds cooled, and the raw building blocks of life dispersed across hundreds of billions of galaxies. The arithmetic is not complicated. It points overwhelmingly to life having emerged countless times in countless locations long before humanity ever walked the Earth. And yet every telescope we aim at the heavens returns the same result. Silence. This is the Fermi Paradox, named for physicist Enrico Fermi, who in 1950 posed a question so fundamental it still rattles the scientific community today. If the universe is this ancient and this immense, and the chemistry of life appears this readily, then where is everyone? Here is what makes the question genuinely disturbing. We are not simply talking about a missing radio transmission from some faraway world. We are talking about the complete and total absence of any detectable evidence of intelligence anywhere beyond Earth. No artifact, no megastructure, no engineered signal. A universe this expansive, this ancient, and this chemically fertile should be teeming with minds. Instead, it appears vacant. To appreciate the full weight of that silence, consider the scale for a moment. Our galaxy alone holds somewhere between 200 billion and 400 billion stars. Astronomers have confirmed that the majority of those stars harbor planets. A meaningful proportion of those planets sit within what scientists call the habitable zone, the orbital range where liquid water can persist on a surface. If even 1 in a million of those planets gave rise to intelligent life, our galaxy alone would contain hundreds of thousands of civilizations, many of them millions of years ahead of us. A civilization just 1 million years more advanced than humanity would have had ample time to explore every corner of this galaxy many times over, even with the technology only modestly beyond our own. The question is not merely where the aliens are. The deeper question is why nothing has reached us. No probe, no transmission, no engineered object drifting through our solar system. That absence demands explanation. Scientists have offered dozens over the decades. Some are comforting. Most are not. They range from the possibility that life is far scarcer than we imagine to the terrifying notion that something systematically prevents civilizations from surviving long enough to make contact. Each explanation carries its own implications for what our future may hold. Before we examine those theories, it is worth sitting with the strangeness of the problem itself. Every time humanity has searched for signals, we have deployed radio telescopes scanning specific frequencies, optical instruments hunting for laser pulses, and automated surveys cataloging anomalous stellar behavior. The searches have been limited, yes, but the silence has been unbroken. Some researchers contend that our search is too narrow, that we are listening for one category of signal in a universe that may communicate through means we have not yet conceived. That is a legitimate criticism, and it makes the problem harder, not easier, to dismiss. What Fermi grasped in 1950, and what keeps researchers sleepless today, is that the silence is not merely curious. It is almost mathematically implausible. The universe had every opportunity to populate itself with minds. Something stopped it. What that something is, and whether it lies behind us or still ahead, is the question that reshapes everything. Because the next theory we are about to examine does not merely describe the silence. It proposes that the silence may be the most critical warning our species has ever received. In 1960, astronomer Frank Drake stood before a chalkboard and inscribed an equation that was never intended to produce definitive answers. It was meant to organize our ignorance. The Drake equation laid out every variable required to estimate the number of communicating civilizations currently present in our galaxy. And, when you work through it with intellectual honesty, it does something unexpected. It reveals precisely where our certainty dissolves and where genuine dread begins. The equation multiplies several factors in sequence. How many stars form in our galaxy each year? How many of those host planets? How many of those planets occupy the habitable zone? Of those, how many actually develop life? Of those, how many evolve intelligent life? How many construct technology capable of communication? And finally, for how long does that civilization persist and broadcast? The initial variables are now reasonably well established. Astronomers have confirmed through decades of study that our galaxy generates roughly 1 to 3 new stars per year. Most host planetary systems. A significant portion contain planets at the appropriate distance for liquid water. These figures, validated by the Kepler Space Telescope and subsequent missions, suggest hundreds of millions of potentially habitable worlds in our galaxy alone. Then the equation strikes a wall. The moment you reach the question of how many habitable planets actually generate life, scientific certainty evaporates entirely. We possess exactly one confirmed example of life in the universe: Earth. Every estimate beyond that is extrapolation built on extrapolation. Some astrobiologists hold that life emerges almost inevitably wherever conditions permit, because the underlying chemistry is so robust. Others maintain that even on Earth, the leap from raw chemistry to a self-sustaining cell may have been a near miracle requiring hundreds of millions of years and extraordinary fortune. That single unknown swings the final answer from millions of civilizations down to precisely one, us. And we have no reliable means yet of knowing which estimate is closer to the truth. But here is where the equation becomes stranger still. Even granting that life arises with some regularity, there is another variable in the formula that quietly consumes everything else. The final term, the lifespan of a communicating civilization. How long does any technologically capable species persist before falling silent? If civilizations typically endure only a few thousand years after attaining radio capability, which is roughly where humanity finds itself right now, the galaxy could be populated with brief flickers blinking on and off, never overlapping in time. 2 civilizations might each exist for 1,000 years, but be separated by millions of years. They would never encounter one another. They would never detect each other. This possibility is known as the temporal spacing problem, and it is among the more quietly chilling resolutions to the Fermi Paradox. Not a dramatic extinction event, not a cosmic predator, just time, vast and indifferent, holding every mind in the universe permanently apart. Drake himself ran the equation at a conference in 1960 and arrived at an estimate of perhaps 10 communicating civilizations in our galaxy. Modern estimates span from below 1 to tens of millions, depending entirely on how generously you fill in the unknowns. That range tells you everything. We are nowhere near resolving this. We are standing at the frontier of what remains unknown. And one of the darkest explanations for why that equation keeps returning low numbers involves what scientists have termed the Great Filter. The Great Filter is not a location. It is not something you can point to in space. It is a concept first formally articulated by economist Robin Hanson in 1998. And it may be the most disturbing idea ever rendered into clean, logical language. The premise is direct. If intelligent life is possible, and the universe is ancient enough to have produced it countless times, but the galaxy appears empty, then something must be eliminating civilizations before they become detectable. Something is preventing life from reaching the stars. The filter might be a single catastrophic threshold, or a succession of smaller ones. It might operate at the chemical level, preventing life from ever starting. It might operate at the biological level, preventing complex cells from forming. It might operate at the cognitive level, preventing animals from developing technology. Or it might operate at the civilizational level, preventing any species from surviving long enough to become interstellar. The terrifying element is not the filter's existence. It is the question of where it falls relative to us. If the Great Filter lies behind humanity, we are extraordinarily fortunate. We already cleared the hardest hurdle, the emergence of life, the evolution of complex cells, the development of intelligence. One of these transitions was so improbable that virtually no other species in the galaxy navigated it. We did, and if that is the case, the path ahead may be genuinely open. We may be among the very few minds in this galaxy, perhaps the only one, with a real future among the stars. But if the Great Filter lies ahead of us, the implications invert entirely. Every civilization that reaches our stage of development eventually encounters a barrier it cannot survive. Nuclear war, ecological collapse, artificial intelligence that escapes meaningful control, some technology not yet conceived turning against the species that created it. In this scenario, the silence of the cosmos is not a puzzle. It is a warning. Every civilization before us approached this threshold and failed. We are approaching it now. There is a way to gauge which scenario is more probable, and the method will unsettle you. Discovering life elsewhere would ordinarily feel like a triumph, but beneath the logic of the Great Filter, it would be a cause for alarm. If we find microbial life on Mars, or complex organisms in the subsurface oceans of a distant moon, or biosignatures in the atmosphere of an exoplanet, it tells us that the emergence of life is not the filter. Life is common, which means the filter must reside further along the path, closer to us, possibly ahead. The more life we discover in the universe, the bleaker our prospects may become. This is an accepted scientific framing. Though the filter itself remains theoretical, no physical law prevents civilizations from spreading. The absence of evidence for any spreading civilization is real, documented, and unresolved. What we do know is this: the silence is real. The mathematics demands an explanation, and whatever is doing the filtering is effective enough to have emptied a galaxy. The next question is whether that filter is a natural property of the cosmos or something far older and more deliberate. The question of whether the great filter lies behind or ahead of humanity is among the most consequential in all of science. Two researchers can examine identical data and arrive at diametrically opposite conclusions, both logically sound, one terminating in hope, the other in something close to dread. The case for the filter lying behind us rests on a chain of biological milestones that each appear, in retrospect, almost absurdly improbable. The first is the origin of life itself. For hundreds of millions of years following Earth's formation, the planet was sterile rock. Life did not spring instantly from available chemistry. It required vast spans of time, and by most accounts a remarkable sequence of molecular accidents. The precise mechanism by which the first self-replicating molecule appeared remains incompletely understood. This is confirmed. Scientists lack a complete model for abiogenesis, the process by which chemistry transitions into biology. But that may not even represent the most difficult step. Roughly 2 billion years after simple bacteria appeared, something stranger happened. One bacterium was absorbed by another cell, and instead of being consumed, became a permanent internal structure. That merger produced the mitochondria. That event produced the complex cell, the foundation of all multicellular life. It appears to have occurred exactly once in 4 billion years of Earth history. Every plant, animal, and fungus alive today descends from that singular, improbable merger. If events of this nature constitute the filter, then we survived them, and the road ahead carries at least some possibility of being navigated. The case for the filter lying ahead is harder to dismiss, and, honestly, harder to sit with. Consider the behavioral pattern of the only civilization we can observe directly, our own. Humanity achieved radio capability roughly 100 years ago. In that same century, we developed nuclear weapons capable of ending civilization, began reshaping the atmosphere in ways that destabilize global systems, and began constructing artificial intelligence whose long-term trajectory no one can fully predict. We are, in the language of risk analysis, a species that acquires catastrophic power faster than it acquires the wisdom to manage it. If this pattern is universal, if every species that reaches technological capability does so before attaining sufficient maturity to handle the consequences, then the filter ahead is not a cosmic accident. It is a developmental trap, a transition every species enters and most do not complete. There is a third possibility that few researchers discuss openly. The filter may not be a single event at all. It may be a sequence of compounding barriers, each one thinning the population of surviving civilizations until the number that achieves interstellar scale rounds to zero. Under this model, no single step destroys everything. But each step reduces the field enough that by the time a civilization could be detected, statistically none remain. This remains theoretical, but it aligns with the data we have. We occupy a specific position on this trajectory. We have cleared the early obstacles, at least partially. Whether the most formidable ones already lie behind us, or whether we are moving toward the edge of the most dangerous threshold any civilization has ever faced, we genuinely cannot say. What we do know is that the next theory offers an entirely different explanation, one that requires no destruction whatsoever. 1998, paleontologist Peter Ward and astronomer Donald Brownlee proposed something that cut against decades of optimistic thinking about life in the universe. Their argument was not that life is impossible elsewhere. It was that complex, multicellular, intelligent life requires such a precise convergence of conditions that Earth may be genuinely extraordinary. Not merely fortunate, but extraordinarily, almost impossibly fortunate. The hypothesis begins with position. Earth does not sit just anywhere in the galaxy. It orbits within what astronomers call the galactic habitable zone, sufficiently distant from the dense, radiation-saturated galactic core, but not so far out that the heavy elements required for rocky planets become scarce. Stars in the galaxy's interior are lashed by gamma-ray bursts and supernova shockwaves far more frequently. Stars in the outer reaches lack the chemical abundance to build complex worlds. Earth sits within a narrow corridor where conditions remain survivable across billions of years. That is only the beginning. Our star is a calm, stable, middle-aged sun that has not significantly altered its energy output in billions of years, providing the continuity required for complex evolution to occur. Many stars are more volatile, more aggressive, or too short-lived for complexity to have a chance. Earth's position within this system is equally unusual. Our large companion moon exerts a gravitational influence that stabilizes Earth's axial tilt. Without that stabilization, our planet's axis would precess chaotically, producing extreme climate swings that would likely have prevented the development of stable ecosystems. Then there is Jupiter. The largest planet in our system acts as a gravitational buffer, capturing or redirecting a substantial fraction of the comets and asteroids that would otherwise strike Earth at far greater frequency. More impacts produce more mass extinctions. More extinctions leave less time for complex life to stabilize and advance. Jupiter's presence may have been indispensable. Add plate tectonics that recycle carbon and regulate temperature across millions of years, a magnetic field that deflects lethal radiation, an oxygen atmosphere generated by early photosynthetic organisms, and the narrow thermal range that kept liquid water stable across billions of years. What emerges is not a picture of a typical world. It is a portrait of an extraordinarily fine-tuned system, in which dozens of factors aligned in precise sequence. Ward and Brownlee argued that while simple microbial life might be widespread in the universe, the full suite of conditions required for complex life is so rare that Earth-like planets capable of producing intelligence might number in the dozens per galaxy or fewer. This hypothesis remains contested. Some astrobiologists push back firmly, arguing that life is adaptive enough to circumvent many of these constraints. But the rare Earth argument remains one of the most scientifically credible responses to the Fermi Paradox. It requires no filter, no catastrophe. It requires only that complexity is genuinely hard to produce. If Ward and Brownlee are correct, the silence has a quiet answer. Not that civilizations rise and collapse, but that the conditions for intelligence were almost never established in the first place. It is a strangely lonely answer, but it may not be the strangest on our list, because the next hypothesis does not suggest that other civilizations failed to emerge. It suggests they emerged, flourished, and made a deliberate choice about us. In 1973, astronomer John Ball proposed something that sounds almost comforting until you examine it closely enough. His idea, known as the zoo hypothesis, suggests that intelligent civilizations do exist in the galaxy, advanced ones, possibly ancient ones, and they know we are here. They simply choose not to make contact. The reason Ball proposed could resemble what we do with wildlife, sanctuaries or uncontacted communities. We observe, we study, we do not intervene. not because we are indifferent, but because we understand that unmanaged contact destroys the very thing you are trying to observe. If a civilization millions of years older than ours decided to monitor Earth, they would have compelling reasons to remain invisible. Consider what happens when a technologically dominant culture makes contact with a less developed one. History provides a consistent answer. The less developed culture is overwhelmed. Its social structures disintegrate. Its belief systems fracture. Its sense of identity collapses. An alien civilization wise enough to have endured millions of years would almost certainly understand this dynamic better than we do. Non-interference may not be indifference. It may be the most ethical possible response to encountering a young, vulnerable civilization. Under this hypothesis, the silence is not emptiness. It is managed restraint. There could be an entire network of elder civilizations that have agreed, formally or through accumulated cultural tradition, to leave developing species undisturbed until some threshold is crossed. That threshold might be a particular level of technological development. It might be a demonstrated capacity for cooperation at planetary scale. It might be something we have not yet achieved and cannot define from our current vantage point. The zoo hypothesis is by its nature extraordinarily difficult to test. If a civilization is sophisticated enough to conceal itself from our instruments, we would have no means of detecting it. Every anomaly we attribute to natural causes could, in principle, be managed. The hypothesis endures precisely because it cannot be falsified. But it raises an uncomfortable follow-up question. If we are in a zoo, what happens as the exhibit evolves? In the past century, humanity has progressed from horse-drawn carriages to nuclear arsenals, to artificial intelligence, to the edge of interstellar communication. If a threshold for contact exists, we may be approaching it faster than anything in our prior history would suggest. And the question of who decides when we are ready and what contact actually looks like when it arrives is one for which we have no framework. Some researchers extend the zoo hypothesis into something somewhat darker. Not a preserve maintained from kindness, but a quarantine maintained from caution. A civilization that has watched younger species destabilize their corners of space might isolate emerging civilizations not for the newcomer's benefit, but for the safety of everyone else. In that version, the silence is not a gift. It is a boundary. This remains theoretical. There is no confirmed evidence of alien observation or management of Earth. But absence of evidence is not evidence of absence, particularly when the entity concealing itself may be millions of years ahead of us in every domain. What we know is that the zoo hypothesis, however unsettling, assumes something almost reassuring, that advanced civilizations survive long enough to become wise. The next theory assumes something entirely different. It assumes that in a galaxy populated with intelligent life, wisdom is a luxury none of them could sustain. The dark forest theory emerges from a thought experiment so bleak it is difficult to sit with. Popularized by Chinese science fiction author Liu Cixin, the underlying logic is not fiction. It is a game-theoretic argument about survival in a universe where resources are finite and intentions cannot be verified. The argument rests on two axioms. First, every civilization's primary drive is survival. Second, the universe does not contain sufficient resources for unlimited expansion by unlimited civilizations. From these two premises alone, the theory draws a devastating conclusion. Imagine you are a civilization that has just detected a signal from another intelligent species. You know nothing about them, accept that they exist and can broadcast. You now face a choice. You could attempt contact and hope for cooperation, but you cannot verify their intentions. You cannot determine whether they are peaceful or predatory. If they are peaceful and you make contact, you gain a potential partner. If they are predatory and you make contact, you have revealed your location to something that may seek to destroy you. If they are peaceful and you eliminate them preemptively, you lose one ally. But if they are predatory and you eliminate them preemptively, you survive. The mathematics of this situation, under assumptions of resource scarcity and the impossibility of verifying intentions across interstellar distances, pushes toward one rational outcome. Strike first, always. Under the dark forest model, the galaxy is not quiet because life is rare, or because civilizations are fragile. It is quiet because every civilization that survives long enough to understand the stakes goes silent. Broadcasting, your existence is not an invitation. It is a death sentence. Every star is a potential predator. Every civilization is a creature moving through the dark, making no sound, leaving no trace, hoping nothing detects it. The implications for our own behavior are disturbing. Humanity has been emitting radio signals for over a century. Those transmissions have already traveled more than 100 light years into space, reaching thousands of stellar systems. If the dark forest model holds, we have already made the gravest possible mistake. More alarming still, certain researchers have proposed that we halt broadcasting immediately. The debate over whether humanity should actively send powerful targeted signals toward distant star systems has grown genuinely contentious among scientists, precisely because of arguments like this one. Stephen Hawking, before his death, publicly warned against it. The dark forest theory is not confirmed science. It is a theoretical framework built on logical premises. Its most significant weakness is the assumption that cooperation is never worth the risk. Some researchers contend that civilizations advanced enough to be dangerous would also be advanced enough to recognize that mutual cooperation offers greater returns than mutual destruction. But that argument assumes rationality scales with technological power. History offers limited support for that assumption. There is also a quieter version of this idea that requires no malice whatsoever, simply the recognition that contact between civilizations of vastly different capability is inherently destabilizing, and that advanced species may go dark not out of aggression, but out of informed caution. Either way, the universe falls silent. And if you believe the dark forest is the most unsettling explanation on this list, what follows makes it look almost peaceful. Every civilization in human history has eventually ended. Empires, cultures, city-states, languages, species. The pattern of rise, flourishing, and collapse is so consistent across the natural and human record that it barely registers as noteworthy anymore. But when you apply that pattern to the Fermi Paradox, it stops being background noise and becomes the loudest conceivable signal. The self-destruction hypothesis holds that intelligent civilizations routinely eliminate themselves before they can make meaningful contact with others. Not through cosmic accidents, not through alien predators, but through their own inventions and their own choices. The timing is what makes this hypothesis so difficult to dismiss. In the roughly 250,000 years that anatomically modern humans have walked the Earth, we spent nearly all of it as small scattered bands with negligible impact on the planet. Then, in the last 12,000 years, we developed agriculture, cities, and organized societies. In the last few hundred years, we industrialized. In the last 100 years, we split the atom, altered the atmosphere, and began constructing artificial intelligence systems that no individual fully comprehends or governs. The acceleration is the problem. With every century, humanity's capacity for accidental or deliberate catastrophe expands faster than our capacity to govern it. Nuclear arsenals exist today capable of ending complex life on Earth. Engineered pathogens are becoming increasingly accessible as biotechnology matures. Climate disruption is already transforming the conditions that support current civilization. And artificial intelligence is advancing along trajectories that even its architects describe as potentially ungovernable. These are not science fiction scenarios. They are confirmed, documented technological realities. The self-destruction hypothesis poses a straightforward question. If this pattern of accelerating capability combined with lagging wisdom is universal among intelligent species, how many civilizations survive the transition from planetary to interstellar reach? If the answer approaches zero, the galaxy fills with brief, brilliant civilizations that incinerate themselves before dispatching a single probe beyond their home system. There is a specific window researchers sometimes call the critical phase. It is the interval between a civilization acquiring planetary-scale destructive power and either developing the wisdom to manage it or the means to escape the planet entirely. On Earth, that window opened roughly in the middle of the 20th century and shows no sign of closing. How long it remains open before something catastrophic passes through it is a question no one can answer with confidence. What makes this especially relevant to Fermi is scale. Even if 99 out of every 100 civilizations survive their critical phase, the galaxy would still contain thousands of survivors. The silence would remain inexplicable. For this hypothesis to fully account for the emptiness, the survival rate would need to be extraordinarily low, possibly approaching zero. And that, when you sit with it honestly, says something profound about us right now in this century. We are not examining a past civilization that failed. We are living inside the critical phase. We are the experiment whose outcome has not yet been determined. Some researchers believe the fact that we are still here, still deliberating, still scanning the heavens, is evidence that something in our nature bends toward survival. Others are considerably less confident. What comes next does not wait for civilizations to destroy themselves. It proposes that something in the galaxy takes a far more active approach. The berserker hypothesis is not a metaphor. It is a specific logical proposition about what a sufficiently advanced civilization might do to guarantee its long-term survival. And once you understand the reasoning, it is very difficult to stop thinking about it. The concept was introduced in science fiction by Fred Saberhagen, but the underlying logic has been taken seriously by researchers in astrobiology and existential risk. The hypothesis proposes that at some point in the galaxy's history, one or more civilizations constructed self-replicating autonomous probes with a single directive: destroy any other civilization you encounter before it can become a threat. To understand why a civilization might pursue this, you have to think across very long time horizons. A civilization that survives tens of millions of years eventually confronts a problem. Other civilizations, if permitted to develop, will eventually reach comparable capability. At that point, the older civilization's dominance is no longer assured. From a purely strategic standpoint, the rational move is to eliminate competitors early before they mature into threats. Rather than waiting for a confrontation at equivalent strength, Self-replicating probes address the problem of scale. You do not need an armada to patrol the galaxy. You build one probe capable of mining raw materials from asteroids, constructing copies of itself, and dispersing. Over millions of years, a single original probe becomes trillions, spreading through the galaxy like a slow, methodical wave. Any planet displaying signs of technological development gets flagged and then eliminated. Under this model, the silence of the universe has a straightforward explanation. We have not been discovered yet. Or perhaps we have, and the clock has already started. That second possibility is not comfortable to dwell on. There is no confirmed evidence of berserker probes, no detected artifacts, no observed destruction events that cleanly fit the profile. But here is the difficulty. If the probes are engineered to be stealthy, we might not recognize them. If they operate on patience, they might wait until a civilization crosses some specific developmental threshold before acting. We would receive no warning. Some researchers have noted that Oumuamua, the enigmatic interstellar object that transited our solar system in 2017, could theoretically fit the profile of a probe. This is not the scientific consensus, which leans toward natural explanations, but the object exhibited behavior that did not entirely match any established natural model, and the question remained open longer than most anomalies do. The berserker hypothesis also provides a grim framework for a pattern in the astronomical record. Several of the most promising nearby star systems for hosting life-bearing planets appear to have experienced significant disruption events in their past. The causes remain debated. What gives the berserker concept its persistence is not any single piece of evidence. It is the logical coherence of the premise. In a universe where survival competition is real and technological capability grows without limit, preemptive elimination is a defensible long-term strategy. It is disturbing precisely because it is rational. The galaxy may not be silent because life is rare or fragile. It may be silent because something already passed through and ensured it. And if that is even partially true, the most important question facing humanity is not how to locate other civilizations. It is whether finding them would be the final thing we ever do. But here is what no one anticipates. The next theory involves no destruction at all. It involves timing, and it rewrites the entire premise. In 2020, a team of astrophysicists, including Robin Hansen, proposed a model that reframes the Fermi Paradox in a way that cuts through most of the speculation. Their framework, which they called the Grabby Aliens model, begins from a single assumption. When civilizations reach a certain level of technological capability, they expand rapidly and permanently. The model does not assume hostility. It does not require self-replication or violence. It simply holds that a technologically mature civilization, given sufficient time, will spread outward through space at a meaningful fraction of light speed, colonizing star systems and leaving behind a visible expanding frontier of transformed space. The central insight concerns timing. If such civilizations existed and began expanding even 1 billion years ago, their expanding boundaries would already have reached us. The galaxy is old enough, and the physics of expansion at even a modest fraction of light speed is rapid enough, that any civilization with a meaningful head start would have made contact by now. Not through a radio signal, but by physically arriving. The fact that we have not been absorbed, contacted, or even grazed by the expanding edge of any such civilization is itself significant data. Under the Grabby Aliens model, this indicates one of two possibilities. Either no such civilizations exist because something prevents them from reaching the expansion phase, or they exist but have not yet launched, meaning we are situated very close in cosmic time to when the first grabby civilizations will emerge, and we might be among them. This second possibility carries a striking implication. If grabby civilizations are rare but inevitable, and if we are close in cosmic time to when the first ones appear, then humanity may be among the very first species to approach this threshold. We are not late arrivals to the gathering. We are early, extraordinarily early. The model predicts that if you surveyed the universe 1 billion years hence, assuming humanity or its successors have expanded, you might observe the cosmos filling with competing spheres of influence originating from multiple civilizations, each growing outward at fractions of light speed, eventually meeting at boundaries and establishing some form of equilibrium or conflict. Right now, the universe appears empty because the expansion age has not yet commenced. The window of silence we observe may be temporary, a cosmic dawn before an extremely loud day. The grabby aliens model has been peer-reviewed and taken seriously in academic circles. It does not resolve every dimension of the Fermi Paradox, but it provides a mathematically coherent answer to the timing question. We detect no expanding civilizations because the expansion era is only just beginning. Whether this is reassuring or alarming depends entirely on your perspective. On one hand, we may simply be first, not trapped in a dangerous cosmos. On the other hand, if we are among the first grabby civilizations to emerge, then the decisions we make in this century about how we expand, what we consume, and how we treat whatever life we encounter will establish a precedent echoing across billions of years of cosmic history. That is not a minor responsibility. But not everyone believes the answer to the Fermi Paradox is written in the stars. Some believe it may be written in the very code of reality itself. And the next theory is arguably the strangest one yet. The simulation argument was formally articulated by philosopher Nick Bostrom in 2003, and it is worth understanding on its own terms before connecting it to the Fermi Paradox. Bostrom's argument does not assert that we live in a simulation. It presents a trilemma. One of the 3 propositions must be true. Either almost all civilizations at our stage of development go extinct before gaining the ability to run detailed simulations of conscious minds, or almost all technologically mature civilizations choose not to run such simulations, or we are almost certainly living inside a simulation right now. The logic is direct. If even a single civilization in the history of the universe survived long enough and elected to run detailed simulations of minds, it could generate an astronomically vast number of them. The simulated minds would vastly outnumber the authentic ones. Therefore, any randomly selected mind, including yours, is statistically far more likely to be simulated than genuine. Now, connect this to Fermi. If we exist inside a simulation, the silence of the universe has a trivial explanation. The sky is vacant because the programmer chose not to populate it. No other civilizations are transmitting because none were rendered with sufficient fidelity to transmit. The universe extends only as far as its observers require. Beyond the edge of our instruments, there may simply be nothing, not empty space, the absence of code. This is not a scientific hypothesis in the conventional sense. It cannot currently be tested, but it is not pure philosophy either. Several physicists have proposed theoretical experiments that might detect the signatures of discretized space-time, the kind of artifact you would expect if physical reality were constructed on a computational grid rather than continuous mathematics. Those experiments have not returned a decisive result. The question remains genuinely open. From a Fermi perspective, the simulation resolution is simultaneously the cleanest and the most structurally disquieting. It requires no great filter, no self-destruction, no alien predators. It requires only that we accept the possibility of a layer of reality above the one we can observe, and that whoever operates that layer chose not to include other voices in our rendering of the cosmos. Some physicists object, noting that simulating a universe with the physical resolution we observe would require computational resources that may be impossible even for an arbitrarily advanced civilization. This is a legitimate objection, but it is not a definitive refutation. We do not know the computational limits of an entity operating outside the constraints of our physics. What makes this theory compelling in the Fermi context is its explanatory economy. The silence is not a puzzle to be solved. It is a design decision. And if it is a design decision, the question transforms entirely. Not where is everyone, but why were we constructed to feel alone? That question has no scientific answer yet. But it has a quality distinguishing it from most Fermi resolutions. It makes the silence feel deliberate, curated, intentional. Whether that prospect is comforting or deeply disturbing likely reveals more about the person contemplating it than about the universe itself. What we turn to next is not philosophy. It is hard biology. And it may be the most grounded, most sobering explanation on this entire list. For most of the 20th century, the dominant assumption in astrobiology was that life, once it begins, tends toward increasing complexity over time. Simple organisms become multicellular. Multicellular organisms develop nervous systems. Nervous systems generate brains. The story appeared to have a natural progression, and Earth seemed to be simply one of billions of worlds ascending it. That assumption has been quietly dismantled over the past 2 decades, not through any single dramatic revelation, but through the accumulation of detail about just how contingent and fragile the path from simple to complex actually was on our own world. Consider the timeline. Life appeared on Earth within a few 100 million years of the planet's formation. That is relatively rapid in geological terms and suggests that the origin of simple life may not be the primary obstacle. Single-celled organisms dominated Earth for approximately 3 billion years. 3 billion years of chemistry, evolution, and environmental pressure, and life advanced nowhere in structural complexity. Then the eukaryotic cell appeared. This is the cell type underlying every complex organism alive today, every plant, animal, and fungus. As noted earlier, this cell arose from a single symbiotic merger between 2 distinct organisms. One cell absorbed another, and rather than digesting it, retained it as a permanent internal energy-producing structure. This gave rise to the mitochondria. Scientists believe this event occurred exactly once across 4 billion years of Earth history. Once in 4 billion years, with no evidence of it occurring anywhere else. After the eukaryote appeared, another billion years elapsed before multicellular life became prevalent. Then came the Cambrian explosion, the geologically abrupt emergence of most major animal body plans, which may have been triggered by atmospheric oxygen reaching a critical threshold. Not a gradual ascent, but a threshold event. Each of these transitions required a specific precondition. The chemistry had to be right. The environment had to be stable long enough. The required random mutation had to occur at exactly the right moment in exactly the right organism. Miss any single one of these, and the progression halts. You get a planet of bacteria indefinitely. Researcher Andrew Knoll of Harvard has spent decades studying early Earth life and argues consistently that the emergence of complexity was neither inevitable nor foreseeable. It was a sequence of accidents stacked upon accidents, each one necessary for the next. From a scientific standpoint, this is not pessimism. It is an honest reading of the fossil and molecular record. If this analysis holds, then the universe is probably not devoid of life. It is probably replete with bacteria, simple organisms thriving in oceans beneath ice shells and in warm subsurface rock formations across thousands of worlds. But the leap to complexity, to nervous systems, to brains, to language and technology, may have occurred only a handful of times across the entire observable universe. Simple life, likely common, confirmed possible on at least one world. Complex life, possibly the rarest phenomenon in existence. The silence of the sky does not mean the universe is dead. It means that complexity is a near impossible accident that happened here and almost nowhere else. And if that is true, the stakes of our survival have just expanded by several orders of magnitude. Because what we explore next is the possibility that not only is complex life rare, but that intelligent technological life may have arisen precisely once. Here. Us. There is a version of the Fermi resolution that requires no catastrophe, no filter, no alien predators, and no simulation. It requires only a particular reading of probability combined with the known age and architecture of the universe. And its conclusion is this: we may be the first intelligent civilization ever to exist anywhere. This idea does not rest on arrogance. It rests on timing. The universe is 13.8 billion years old. For roughly the first 9 billion of those years, the conditions required for complex rocky planets like Earth were not yet established. The first generation of stars contained almost no heavy elements. They burned intensely and died rapidly, seeding the cosmos with carbon, oxygen, iron, and the other atoms necessary for chemistry and biology. Only after multiple generations of stellar birth and death did enough of those elements accumulate to construct the kind of world Earth represents. Our planet formed approximately 4 billion years ago. Complex life required over 3 billion years to emerge. Technological intelligence required another several hundred million years beyond that. Furthermore, when you situate humanity on the timeline of cosmic chemical enrichment, we appear at nearly the earliest possible moment that beings like us could exist. Not billions of years late to a crowded gathering, right at the threshold. If the emergence of intelligence requires the heavy element abundance that only became widespread roughly 5 to 8 billion years ago, and if intelligence also requires several billion years of biological evolution to develop, then there is a narrow window at the leading edge of possibility where the first minds could arise. We may be residing in that window right now. Under this framing, the universe is not yet old enough to be full of intelligence. We are not survivors of a galactic purge. We are not undiscovered by a wiser civilization. We are simply early, among the very first in a universe, only just reaching the conditions where such arrivals become possible. The implications are vast. If we are first, everything that follows is an unwritten page. There is no elder civilization to learn from, no established template, no cautionary account from a predecessor who already made the catastrophic errors. We inscribe the first marks in what may eventually become a cosmos populated with intelligence, but only if we endure long enough to pass something forward. This is not a confirmed conclusion. It is a theoretical possibility consistent with current cosmological evidence. Researchers like David Kipping at Columbia University have published work suggesting that the distribution of intelligence emergence times across the universe may genuinely favor very early emergence for the first civilization, placing us at or near that leading edge. The solitude of this hypothesis differs from other Fermi resolutions. It is not the solitude of the final survivor. It is the solitude of the first arrival. A universe dense, with potential, none of it yet expressed, and us standing at the beginning of something that has never before occurred. There is a gravity to that. If we are first, the survival of Earth civilization is not merely our concern. It is the sole thread connecting the universe to the possibility of a future filled with minds. And, if that is not enough to absorb, the next chapter introduces something suggesting that our search strategy itself may be the fundamental problem. The search for extraterrestrial intelligence has been dominated for decades by a single method: radio telescopes aimed at specific frequencies, listening for structured signals that natural processes would not generate. This approach began formally in 1960 with Project Ozma and has continued through various programs ever since. It is reasonable, it is scientifically defensible, and it may be missing the point entirely. Here's the problem. Radio waves disperse as they travel. Energy spreads across an ever-expanding sphere of space. By the time a signal has journeyed a few hundred light-years, it has diluted to a level extraordinarily difficult to separate from the background noise of the universe. Our own most powerful deliberate transmission, the Arecibo message dispatched in 1974, would be essentially undetectable to current human technology at even a fraction of the distance to the nearest stars. This means that even if hundreds of civilizations were broadcasting with technology equivalent to ours, we would almost certainly not detect them across interstellar distances. Radio is not an effective interstellar communication medium for civilizations at our developmental level, and civilizations significantly more advanced may have abandoned it long ago. Consider humanity's own trajectory. We have been emitting strong omnidirectional radio signals for roughly a century. But trends in communication technology are already shifting away from high-powered, broadly dispersed transmission toward tightly focused, encrypted digital communication. Powerful broadcast signals are giving way to fiber optic networks and direct link systems. As a civilization's communication infrastructure matures, it tends to become quieter and less detectable from the outside. An advanced civilization might be effectively invisible to radio-based searches, not because it stopped communicating, but because it evolved toward communication modes we have not yet developed. Tightly focused laser pulses, neutrino-based transmissions, gravitational wave modulation. Any of these would pass through our current instruments without leaving a recognizable signature. What researchers increasingly advocate is a shift toward what they call technosignatures, evidence of technology that persists and scales beyond what individual broadcasts can offer. Heat signatures from industrialized worlds. Atmospheric chemistry inconsistent with any natural model. Structured light curves from stars with engineered objects in orbit. These indicators would be harder to conceal and would not require a civilization to be actively attempting communication. The logic is compelling. If you want to locate a city, you do not listen for phone calls. You look for lights from above. Our current search strategy is the equivalent of listening for phone calls across an ocean, while the city we seek stopped using phones a century ago. The silence we hear may have nothing to do with absence. It may have everything to do with the limitations of our instruments and the assumptions embedded in our methods. This is an area of active, ongoing scientific discussion. It is not a fringe position. It is central to the current direction of astrobiology research and is increasingly shaping how funding institutions prioritize investigations. And, speaking of things we may have already observed without recognizing them, the next section concerns one of the most celebrated anomalies in the history of this entire search. A signal that appeared once, persisted for 72 seconds, and has never been explained. If a civilization advanced enough to construct structures visible from across the galaxy exists, it would almost certainly not announce itself through a radio broadcast. It would announce itself by reshaping its environment on a scale so enormous that the evidence would be encoded in the light of distant stars, detectable by any civilization patient enough to observe it. This is the logic underlying the study of technosignatures, the search for physical evidence of technology rather than deliberate communication. And the focal object of that search is the Dyson sphere. Physicist Freeman Dyson proposed in 1960 that a civilization confronting energy constraints would eventually recognize the most obvious available source, the complete output of its star. A sufficiently advanced civilization would construct a structure, not necessarily a solid shell, but perhaps a swarm of orbiting collectors and habitats that captures a significant fraction of its star's energy. From outside, a star enclosed by a Dyson swarm would appear anomalous. It would emit less visible light than expected for its mass and classification, while radiating excess energy in the infrared spectrum. That specific signature, abnormally low visible output combined with abnormally elevated infrared emission, is something our instruments can detect across thousands of light years. Astronomers have catalogued candidates. None have been confirmed as artificial, but the search has only recently become systematic. The Gaia mission, the Wide Field Infrared Survey Explorer, and forthcoming missions like the Nancy Grace Roman Space Telescope are generating stellar catalogs at a scale that makes systematic technosignature searches viable. For the first time, researchers are deploying machine learning to identify stars behaving in ways inconsistent with established natural models, searching for irregular, structured dimming patterns that an incomplete or partially assembled megastructure might produce. Beyond Dyson spheres, researchers are examining other engineering signatures. Stars losing mass in non-standard ways might be hosting planetary-scale mining operations. Planetary systems with unusual orbital configurations might have been deliberately reorganized. Gas giants stripped of their outer layers might bear evidence of resource extraction at civilizational scale. None of these have been confirmed, but the scientific community increasingly accepts technosignature research as a legitimate and necessary component of any serious search for extraterrestrial intelligence. NASA formally funded technosignature research beginning in 2019, representing a significant institutional shift. One particular class of technosignature has generated extraordinary scientific attention: starlight that dims in irregular, non-periodic patterns. Not the clean repeating signals of a transiting planet or binary companion, but complex fluctuations varying in depth, duration, and profile from one event to the next. This pattern is not what any known natural object consistently produces, and it has been observed in a real stellar system. The star responsible lies roughly 1,500 light-years distant. Its behavior has generated more peer-reviewed papers, more competing hypotheses, and more genuine scientific controversy than almost any other single object in the past decade. What is occurring around that star, and why scientists still cannot fully converge on a natural explanation after years of intensive observation, is the subject of the next section. The longer you examine the data, the harder it becomes to feel settled. On August 15, 1977, a radio telescope at Ohio State University recorded something unusual. The instrument was part of a program called Big Ear, one of the earliest organized searches for extraterrestrial radio signals. It scanned the sky automatically, printing columns of data onto continuous paper. A volunteer named Jerry Amon was reviewing the printouts days later when he encountered a sequence of numbers and letters that stood apart from everything surrounding it. The signal lasted exactly 72 seconds, the full duration the telescope's field of view could hold any given point in the sky. It appeared to originate from the direction of the constellation Sagittarius. It possessed the intensity, the frequency, and the narrowband structure that researchers had theoretically predicted an artificial extraterrestrial signal might display. Amon circled the data and wrote a single word in the margin. Wow! The signal has never been detected again. Dozens of follow-up observations have targeted the same region of sky using more capable instruments across the past nearly 50 years. Nothing has returned. No repetition, no faint echo, no corroborating detection from any other telescope during the same window. Whatever produced it either appeared once and moved on or simply ceased. This is confirmed observational data. The signal was real. Its characteristics are genuinely unusual. What generated it remains entirely unknown. Over the decades, several natural explanations have been proposed. A comet releasing hydrogen gas in a specific orientation was among the more recent candidates, advanced by astronomer Antonio Paris in 2017. His hypothesis attracted significant attention and equally significant skepticism. Multiple researchers examined his analysis and found that the comets he identified would not have been positioned correctly to produce the observed signal, and that the hydrogen gas explanation did not adequately account for the signal's narrow-band character. The comet explanation has not been accepted as definitive by the broader scientific community. The WOW signal occupies a rare and uncomfortable scientific category, an anomaly with no confirmed natural explanation, but equally no confirmed artificial one. It is not proof of extraterrestrial intelligence. It is an unexplained data point, and science must operate honestly within that distinction. What makes it particularly striking is the frequency. The signal appeared near 1,420 megahertz, the emission frequency of neutral hydrogen, the most abundant element in the universe. Decades before the detection, researchers had argued that this frequency would be the logical choice for any civilization attempting interstellar contact, a universal radio landmark that any species studying the cosmos would recognize. The WOW signal appeared precisely there. Whether that is an extraordinary coincidence or something more significant, science cannot currently determine. What it can affirm is that nearly 50 years of follow-up observation have not produced a satisfying natural explanation. That absence of explanation is not evidence of extraterrestrial origin. But it is evidence that we encountered something our models have not fully accounted for. One observation, one marginal annotation. Nearly 50 years of silence from the same patch of sky. If the WOW signal was the most celebrated single anomaly of the last century, the next one arrived more recently, persisted for years rather than seconds, and generated a level of scientific bewilderment the field had not experienced in decades. In 2015, a paper by astronomer Tabitha Boyajian and a team of collaborators described a star approximately 1,400 light-years away exhibiting behavior no natural model could cleanly explain. The star, formerly catalogued as KIC 8462852, but now almost universally known as Tabby's star, was dimming. Not in the regular periodic pattern produced by an orbiting planet, not in the smooth, predictable curve of a binary companion. It was dimming in complex, irregular bursts, sometimes by as much as 22% over the course of days, then brightening, then dimming again in an entirely different pattern. 22% is an enormous dimming event for any star. A Jupiter-sized planet, among the largest natural objects that could transit a star, blocks roughly 1% of stellar light. Whatever was occluding Tabby's star was by any natural standard impossibly large, and it was not periodic, not symmetric, and not consistent with any known category of orbiting body. The data originated from the Kepler Space Telescope, which monitored over 150,000 stars simultaneously for planetary transits. Over 4 years of observation, Tabby's star produced the most anomalous light curve in the entire dataset. Citizen scientists participating in the Planet Hunters project flagged it as something they had never encountered. Their instinct was correct. Naturally, researchers initially examined the most dramatic possible explanation. The irregular dimming pattern is precisely what you might anticipate from a Dyson swarm. A collection of large orbiting structures at various stages of assembly, blocking varying amounts of light at different times as components move through the line of sight. This was not fringe speculation. It appeared in peer-reviewed publications and was taken seriously by multiple researchers. The scientific community did not ultimately settle on that explanation. This is confirmed following years of intensive observation. The most widely accepted current hypothesis holds that a cloud of disintegrating dust and debris, possibly the remnants of a shattered comet family, or a disrupted planetesimal belt, accounts for the irregular dimming. But this explanation carries its own unresolved difficulties. The scale and structure of the dimming events remain difficult to fully explain with available natural models. More recently, astronomers found that Tabby's star also exhibits a long-term gradual dimming trend spanning years, a slow decrease in overall brightness entirely separate from the acute transit events. This long-term behavior is also anomalous, and adds another dimension of complexity to any proposed explanation. Tabitha Boyajian herself has been careful and measured in her public statements, consistently emphasizing that the most probable explanation is natural, and that no evidence of artificial construction has been confirmed. That scientific caution is appropriate. But she has also consistently acknowledged that the object has not been fully explained. What makes Tabby's star significant in the Fermi context is not any particular claim about its nature. It is what the object demonstrates methodologically. For the first time, astronomers found a real stellar system exhibiting behavior that, without any predisposition toward dramatic conclusions, a technosignature researcher would have flagged as a candidate warranting serious investigation. The instruments functioned. The anomaly was genuine. The natural explanation remained incomplete. That is not a discovery of alien technology, but it is a demonstration that searching for it in this manner might actually work. And if Tabby's star left researchers unsettled, the next anomaly did something far stranger. It did not remain in a distant system and dim. It traveled through our own solar system. It moved, and it refused to behave like anything ever previously catalogued. In 2007, astronomers reviewing archival data from the Parkes Radio Telescope in Australia discovered something that should not have been there. A burst of radio energy lasting only a few milliseconds, with an intensity so extreme it had to have originated from beyond our galaxy. The burst was so brief, so powerful, and so structurally unusual that the researchers spent years verifying it was not instrument error before publishing. It was not instrument error, and it was not alone. Since that initial detection, astronomers have catalogued hundreds of fast radio bursts, brief flashes of radio energy lasting anywhere from a fraction of a millisecond to a few seconds. Each releases more energy in that instant than our star emits across several days. They arrive from random directions across the sky, suggesting sources distributed throughout the universe rather than concentrated in any particular region. Their precise physical origin was for years entirely unknown. What deepened the mystery was repetition. Most fast radio bursts appeared once and never recurred. Then researchers discovered a small subset that repeated, sometimes irregularly, sometimes in structured cycles. One source catalogued as FRB 121102 has been observed to repeat in bursts that cluster periodically, then fall quiet, then cluster again. The period of that cycle is approximately 157 days. Regular enough to suggest an underlying mechanism. Irregular enough to resist simple explanation. The leading scientific explanation today points to magnetars, highly magnetized neutron stars that rank among the most extreme physical environments in the known universe. A magnetar can release enormous quantities of electromagnetic energy during starquake events, when stresses on its rigid crust cause sudden fractures. In 2020, astronomers detected a fast radio burst from a magnetar within our own galaxy, the first time such an event was confirmed to have an identified source. This was a meaningful scientific milestone. It established that magnetars can produce at least some fast radio bursts. But it did not close every open question. The energy levels of some observed bursts, particularly those arriving from distant galaxies, exceed what current magnetar models predict under standard physics. The structured periodicity of repeating sources remains incompletely explained. The sheer variety in burst characteristics, profiles, durations, frequencies, and repetition patterns suggests that a single source class may not account for everything in the catalog. Some researchers have explored whether a subset of fast radio bursts could represent technosignatures. The energy required to produce a burst at the intensities we detect from extragalactic distances is so extreme that if it were artificial, the engineering involved would dwarf anything conceivable today. Physicist Avi Loeb of Harvard has proposed that a sufficiently powerful artificial emitter, designed for interstellar propulsion rather than communication, could theoretically produce a fast radio burst as a byproduct. He calls this the lighthouse model. This is not the scientific consensus. It is a theoretical possibility raised by a credentialed researcher and not yet eliminated. What fast radio bursts confirm, regardless of their origin, is that the universe contains physical processes generating structured energetic emissions on timescales and at intensities we are only beginning to characterize. Every time we have opened a new observational window on the cosmos, we have encountered things we did not anticipate. Fast radio bursts were invisible to us 2 decades ago. What else remains currently invisible? But compared to what entered our solar system in 2017, fast radio bursts feel safely remote. What came next did not maintain a polite extragalactic distance. It came directly to us. On October 19, 2017, an astronomer at the Haleakala Observatory in Hawaii detected a fast-moving object traversing our solar system. Initial calculations suggested it was a comet from our own neighborhood. Closer analysis revealed something that stopped the field entirely. The object had originated from outside the solar system. It was the first confirmed interstellar visitor ever detected. They named it Oumuamua, a Hawaiian word meaning roughly a messenger from afar arriving first. Initially, astronomers anticipated a straightforward classification: an interstellar rock or icy body ejected from some distant stellar system and drifting through space for millions of years before a chance gravitational encounter brought it through ours. The universe is ancient. Ejected debris should be abundant. Finding one passing through was surprising but scientifically manageable. Then the data, returned and manageable, became inadequate. Oumuamua was shaped unlike any natural object previously catalogued. Estimates based on its reflectivity and brightness variation suggested it was extremely elongated, with a length-to-width ratio of perhaps 10:1 or more. No known natural formation process reliably produces objects with that geometry at that scale. Comets are irregular, but not blade-like. Asteroids vary, but not so dramatically. The shape alone was anomalous. Then came the trajectory problem. As Oumuamua moved away from our star, it accelerated, not dramatically, but measurably and persistently, beyond what gravity alone could account for. Comets accelerate this way when heat from a nearby star vaporizes subsurface ices, creating outgassing jets that propel the object. This is well understood. Astronomers searched for signs of outgassing. They found none. No detectable gas cloud, no dust trail, no coma, just clean, unexplained acceleration. Every proposed natural explanation for the anomalous acceleration has been published and subsequently challenged. One hypothesis suggested it was composed of hydrogen ice, which would outgas invisibly. The problem: hydrogen ice is not stable in the interstellar environment long enough to survive the journey implied by its trajectory. Another suggested it was a thin, flat piece of natural material propelled by radiation pressure from our sun, like a natural solar sail. The problem: an object thin enough to be accelerated that way by light would need to be no more than a millimeter thick across a surface hundreds of meters wide, a geometry for which no natural formation mechanism is known. A.V. Loeb of Harvard, one of the most prominent astrophysicists in his field, argued publicly and in a published book that the most parsimonious explanation for Oumuamua's properties taken together was that it was artificial. Not that it was certainly artificial, but that, given the accumulation of anomalies, the hypothesis warranted serious scientific examination rather than reflexive dismissal. The mainstream scientific community disagreed, largely maintaining that a natural explanation would eventually emerge. In 2023, researchers proposed a new mechanism involving nitrogen ice fragments from a shattered exoplanet surface, which could theoretically reproduce the observed characteristics. This explanation received attention, but has not achieved universal acceptance. What Oumuamua confirmed, regardless of its origin, is that interstellar objects pass through our solar system, and that at least one of them behaved in ways our models did not predict. A second interstellar object, Borisov, arrived in 2019 and behaved entirely normally, exactly as a comet should. The contrast only deepened the strangeness of the first. The full account of Oumuamua remains open. The object is long gone, now too distant for any instrument to reach or observe. Whatever it was, it passed through and left us with questions we still cannot answer. And if something from outside our solar system could arrive unannounced and depart without explanation, it forces a harder question. What else might be out there that we lack the tools to recognize? One of the quieter resolutions to the Fermi Paradox requires no rare life, no destroyed civilizations, and no hiding. It requires only that the universe is physically structured in a way that makes traversing it fundamentally prohibitive for any civilization, regardless of how advanced. And the more carefully you examine the physics, the harder it is to set aside. The first obstacle is energy. To accelerate a spacecraft to even 1/10 of light speed, the minimum velocity considered meaningful for practical interstellar travel within a human lifetime, requires an energy expenditure that dwarfs anything our civilization currently produces. For a vehicle of modest spacecraft mass, the energy required approaches what would be released by thousands of nuclear detonations merely to reach that fraction of light speed. Scale the vehicle up. Add life support systems, fuel reserves, and shielding, and the energy requirements become staggering. Then there is the fuel paradox. Any rocket-based system must carry its own propellant, but propellant has mass. Greater mass requires more fuel to accelerate it. The relationship is exponential, not linear. As mission distances grow, the required fuel mass rapidly reaches absurd proportions. Chemical rockets are plainly inadequate. Nuclear propulsion improves the situation but does not resolve it. Fusion drives, if achieved, would help substantially. But even under optimistic fusion scenarios, the engineering required for a rudimentary interstellar mission represents centuries of advancement beyond our current capability. The second obstacle is time. Even at 1/10 of light speed, the journey to the nearest confirmed stellar system, Proxima Centauri, takes approximately 40 years. The nearest star systems that might host Earth-like planets lie farther still. For a civilization attempting to survey a galaxy 200,000 light-years across, the timescales involved are nearly impossible to internalize. Even dispatching probes at significant fractions of light speed across the full breadth of the galaxy would require millions of years. Civilizations waiting for their probes to return, or their colonies to report back, would require institutional continuity across timescales that exceed the entire recorded history of human civilization thousands of times over. The third obstacle is collision risk. At high velocities, interstellar space is not empty. Dust grains and microscopic particles, invisible and essentially undetectable at interstellar distances, become lethal at relativistic speeds. A particle no larger than a grain of sand encountered at a significant fraction of light speed carries the kinetic energy of a small explosive device. Shielding against such impacts across decade-long journeys is an engineering challenge with no current solution. These barriers are real. They are confirmed by physics. They do not yield to optimism or clever narrative framing. What they imply for the Fermi Paradox is that even civilizations far in advance of us may have concluded that physical interstellar travel is not viable as a general strategy. The galaxy may be inhabited by intelligent species that have never departed their home systems, not for lack of will or curiosity, but because the physics simply does not cooperate. In that scenario, the silence is not evidence of absence. It is evidence of confinement. Each civilization locked within its own small sphere of space, perhaps listening, perhaps broadcasting, but unable to bridge the distances separating them. If that confinement is real and universal, the next question becomes stranger still. Could a civilization leave a detectable mark without physically traveling? And do any such marks already exist that we have not yet learned to interpret? Most discussions of the Fermi Paradox treat the problem as a spatial one. Where are they? Why have they not come here? But there is an equally powerful version of the same problem that operates entirely in time. And it may be more unsettling than any of the spatial arguments. The universe is 13.8 billion years old. Complex life on Earth required roughly 4 billion years to produce intelligence. If the emergence of intelligence is even moderately probable given suitable conditions, and if those conditions existed elsewhere in the galaxy several billion years before they existed on Earth, then there may be civilizations whose entire rise, development, and possible extinction occurred billions of years before a single human ancestor stood upright. A civilization that peaked 2 billion years ago would leave no radio signals detectable today. Its broadcasts, if they ever reached our region of space, passed through billions of years ago, when the only life on Earth was single-celled organisms with no instruments and no awareness. Any physical artifacts they launched into space would by now be indistinguishable from natural debris, transformed and redistributed by billions of years of cosmic processes. The inverse is equally true. Civilizations that will arise in the future, millions or billions of years hence when stellar conditions have evolved further, will emerge long after we are gone. From their perspective, we will be the ancient and silent ones. Our transmissions will have faded. Our artifacts, if any survive, will be incomprehensible relics. This is sometimes called the temporal communication problem. Two civilizations can inhabit the same galaxy and yet be so separated in time that they never have the opportunity to detect each other's existence. The overlap required for detection is not merely proximity in space. It is proximity in time, and on cosmic scales, that is a far narrower window. Astronomer Milan Cirkovic has written extensively on this idea, arguing that our search for extraterrestrial intelligence rests on an implicit assumption that civilizations exist on timescales comparable to ours. If civilizations can persist for millions or billions of years, the galaxy's history of intelligence may be largely in its past, not its present. We may be searching for something that flourished and faded long before our instruments existed. There is also a forward-looking version of this argument containing its own disturbing implication. If intelligence is genuinely rare and we are among the first to emerge, then the full flowering of minds in this universe may lie tens or hundreds of millions of years in the future. We are not late arrivals to a sparse gathering. We are among the very earliest, and the gathering itself has barely commenced. Whether that framing feels hopeful or isolating probably depends on the day you are having. What it does accomplish is to shift the question from where is everyone to when is everyone, and in doing so, it dissolves the urgency from the silence. The galaxy may not be empty. It may simply be early. But there is a different category of civilization that might exist right now, in this moment, that no telescope can locate. Not because they are concealed, not because they have been destroyed, but because they never developed any technology we would recognize as a signal. There is an assumption so deeply embedded in the search for extraterrestrial intelligence that it is rarely examined directly. The assumption is that intelligence leads inevitably to technology, that any species capable of abstract reasoning will eventually construct machines, generate electromagnetic signals, and leave a detectable impression on its environment. Earth's history supports this, but Earth's history represents a sample size of 1. Consider the cognitive sophistication of some Earth species that never developed technology. Dolphins have demonstrated self-recognition, intricate social structures, regional dialects, and problem-solving capabilities that would have seemed remarkable to earlier generations of researchers. Elephants grieve their dead, maintain multi-generational social memory, and coordinate in ways suggesting genuine strategic awareness. Crows and ravens manufacture tools, plan for future contingencies, and recognize individual human faces, distinguishing trusted individuals from potential threats across years. Octopuses display problem-solving and learning behaviors that evolved in complete independence from vertebrate intelligence, suggesting that cognitive sophistication can arise through radically different biological pathways. None of these species are constructing radio transmitters. Intelligence and technological civilization are not the same phenomenon. Intelligence is a cognitive trait. Technological civilization is a specific cultural and biological trajectory that depends on a cluster of factors that may not be universal. Hands, capable of precise manipulation. Social structures enabling large-scale cooperation and knowledge transmission. Sufficient environmental pressure to drive innovation rather than stability. A metabolism and lifespan that rewards long-term investment in tools. Remove any of these from the equation, and you can have a world full of intelligent beings living rich, complex, cognitive lives while leaving essentially no detectable trace from space. An ocean world, for example, could sustain enormous populations of intelligent marine organisms with no access to fire, no capacity to smelt metal, and no pathway to electronics. Their intelligence might be profound. Their civilization, by any internal measure, might be sophisticated and ancient. From space, their world would appear as a featureless water body. This possibility scales uncomfortably well. If even a significant fraction of worlds hosting intelligent life contain species that never develop detectable technology, the silence resolves, without any filter, any catastrophe, or any concealment. The universe may be full of minds we simply cannot perceive, because we are looking exclusively for the specific technological signatures our own trajectory produced. Some astrobiologists have begun taking this seriously enough to propose that the definition of intelligence employed in the search for extraterrestrial intelligence is too restrictive. We are not searching for intelligence. We are searching for industrial civilization, and there is no guarantee that intelligence and industry travel together across all conceivable biospheres. This does not resolve the deeper question. Even one civilization that developed technology in 4 billion years of Earth history managed it. Statistically, that seems like it should occur elsewhere. But the argument from non-technological intelligence adds another stratum to the silence. Some of what we are not hearing may not be silence at all. It may be a conversation in a language we have not yet imagined. And the next stratum of that idea runs deeper still. Because even among species that do develop technology, The fundamental architecture of their minds might make it impossible for us to recognize what they are constructing or communicating. In the last decade, the catalog of potentially habitable worlds in our solar system has expanded dramatically. Not through discoveries of Earth-like rocky planets with thin atmospheres and open skies, but through something entirely different. Worlds harboring liquid water concealed beneath thick outer shells of ice, insulated from the cold of space by the pressure of kilometers of frozen crust. These ocean worlds are now considered among the most promising candidates for life in our solar system and possibly across the universe. Europa, one of Jupiter's moons, is estimated to contain twice the total volume of liquid water present across all of Earth's oceans. It lies beneath an ice shell potentially dozens of kilometers thick, kept warm not by sunlight, but by tidal flexing generated by Jupiter's immense gravitational influence. The seafloor may host hydrothermal vents analogous to those on Earth, where chemical energy rather than light sustains ecosystems in total darkness. Life exists around Earth's hydrothermal vents completely independently of sunlight. This is confirmed. Enceladus, a moon of Saturn, actively ejects plumes of water vapor and ice particles from its southern polar region. Analysis by the Cassini spacecraft detected molecular hydrogen, silica, and organic compounds within those plumes. The chemical signatures of hydrothermal activity and the molecular building blocks of biology. Enceladus is actively venting material from its subsurface ocean into space. Whatever inhabits that ocean is, in a sense, already reaching us. Titan, also orbiting Saturn, offers a different kind of liquid environment. Dense hydrocarbon lakes on its surface suggest the possibility of chemistry-based life operating on entirely different principles than water-based biology. Titan's atmosphere is thicker than Earth's and saturated with organic compounds. Researchers have proposed theoretical metabolisms that could function in liquid methane rather than water. Now consider the Fermi implications. A civilization that evolved within a sealed subsurface ocean beneath kilometers of ice faces a nearly insurmountable barrier to any form of space-based communication or exploration. They would have no access to the electromagnetic sky above them. No stars, no radio frequencies, no line of sight to anything beyond their world. Their entire observable universe would consist of the ocean surrounding them and the rock beneath. Even if such a civilization developed intelligence, language, culture, and sophisticated technology adapted to their environment, the path to radio transmission or space exploration would require them to first comprehend that a universe existed above their ice ceiling. Then penetrate kilometers of solid ice, then survive in a vacuum for which nothing in their biology or experience had prepared them. The obstacles are not merely engineering problems, they are conceptual ones. A civilization that has never observed a star does not naturally arrive at the idea of broadcasting into space. Thousands of ocean worlds may exist across the galaxy right now, some harboring complex life, perhaps intelligent life, locked in silence beneath their shells. Not silent by choice, silent by architecture. This matters enormously for how we conceive of the Fermi Paradox. If a substantial fraction of habitable environments in the universe are enclosed rather than open, the pool of civilizations capable of electromagnetic communication is far smaller than the pool of civilizations that actually exist. We are not simply searching for life. We are searching for a specific subset of life that happened to evolve in an environment compatible with the particular kind of curiosity that builds telescopes. But even among civilizations that do have access to open skies and vast electromagnetic possibility, there may be a barrier just as impenetrable as a kilometer of ice. A barrier constructed not of rock or vacuum, but of cognition itself. When we search for extraterrestrial intelligence, we are searching for something that resembles our own intelligence closely enough that we can identify it. Structured mathematical sequences, consistent frequency patterns, artifacts exhibiting geometric precision. The implicit assumption is that intelligence produces recognizable order, but that assumption has never been tested against anything other than human intelligence. Our concept of what constitutes a signal is built entirely on what our own minds generate. We look for prime number sequences because we would broadcast prime numbers. We flag anomalous geometric structures because we construct geometric structures. The entire search methodology is, at its foundation, a projection of human cognitive style onto a universe we have never actually sampled for cognitive diversity. Consider what a genuinely alien intelligence might look like. Not an intelligence that shares our evolutionary pressures, our sensory modalities, our social structures, or our relationship with time. Something that developed under fundamentally different constraints on a fundamentally different world. Perhaps with multiple simultaneous processing streams rather than a single linear thread of consciousness. Perhaps with a relationship to information storage and retrieval that operates across a biological substrate. Nothing like our nervous system. There is no guarantee such an intelligence would produce anything we recognize as structured communication. Its artifacts might appear to our instruments as natural noise. Its signals might convey information across dimensions we do not monitor. Its technology might operate on physical principles we understand theoretically but have never observed in application. We would examine the evidence directly and perceive nothing, not because nothing is present, but because we lack the cognitive or instrumental framework to interpret it. Researchers studying animal cognition have encountered small versions of this problem here on Earth. For decades, animal communication systems were evaluated by whether they resembled human language. Species that did not meet that criterion were classified as non-linguistic. As researchers developed new frameworks for analyzing non-human communication, previously invisible complexity emerged. Prairie dog vocalizations have been shown to encode surprisingly specific information about predator characteristics. Whale song contains structural features sharing certain mathematical properties with human language. Bee dances communicate distance and direction through a physical medium no human sensory system can directly interpret. These are animals sharing billions of years of evolutionary history with us. An alien intelligence sharing none of that history might be so fundamentally distinct in cognitive architecture that the gap is not a matter of translation, but of category. The instruments we construct to listen are calibrated to patterns our minds can process. Patterns our minds cannot process will pass through those instruments invisibly. This is a genuinely sobering scientific observation. The Fermi Paradox may not be posing the right question. The question is not, where is everyone? It may be whether we could identify everyone even if they were, in some sense, present. The silence might represent a communication breakdown at the deepest conceivable level, not a failure to transmit, but a failure to perceive. And if that cognitive barrier applies to what we can receive, it applies equally to what we can transmit. Any message we broadcast is constructed to the specifications of a human mind. Whether it carries meaning for a radically different kind of intelligence is a question we cannot answer from the inside. This leads to one of the most unsettling ideas on this list. Not that intelligence is out there in concealment, not that it arose and faded, but that it may have arrived here long ago and left something behind. Something we have been looking at for billions of years without understanding what it is. In 1973, molecular biologist Francis Crick, who shared the Nobel Prize for co-discovering the structure of DNA, published a scientific paper with astronomer Leslie Orgel, proposing something the scientific establishment received with considerable skepticism. Their hypothesis, which they called directed panspermia, suggested that life on Earth did not originate here through purely natural chemistry. It was deliberately seeded by an extraterrestrial civilization. Crick arrived at this idea not through mysticism, but through biochemistry. He was troubled by what he perceived as the extreme improbability of life's spontaneous generation from raw chemistry within the time window available on early Earth. Life appeared remarkably quickly after Earth's surface cooled. The genetic code is also extraordinarily universal, a single coding system shared by every known form of life on Earth, from bacteria to redwood trees to humans. Crick found this universality suspicious. It implied either a single common origin or deliberate design employing a standardized system. Directed panspermia proposes that a sufficiently advanced civilization, confronting the eventual death of its star or other existential pressures, might have seeded numerous worlds across the galaxy with microbial life or the chemical precursors to life. Not to colonize, not to communicate, but simply to propagate biology as widely as possible, ensuring that wherever conditions eventually became favorable, life would begin. If this hypothesis is correct, it substantially reframes the Fermi Paradox. The origin of life on Earth might not be an independent data point at all. It might be evidence of a prior civilization that no longer exists, or exists in a form we do not recognize. The silence we observe would be the silence of an ancestor, a civilization that may have peaked billions of years ago, seeded what it could, and then faded. The hypothesis is by its nature nearly impossible to confirm or refute. The genetic code's universality can be explained by common descent from a single origin point without invoking extraterrestrial agents. The rapid appearance of life on early Earth, while surprising, has proposed natural explanations that Crick's critics considered adequate. What the hypothesis productively accomplishes is to force a different kind of question about the search for life. If panspermia, directed or natural, is a real mechanism, then discovering life elsewhere in the galaxy would not necessarily indicate an independent origin. Two worlds with life might share a common biological ancestry, either through natural transport of material between star systems during early solar system formation, or through deliberate seeding by a civilization for which we have no other evidence. A recent area of research supports at least the natural version of this concept. Rocks ejected from planetary systems during formation can traverse interstellar distances over millions of years, occasionally landing on new worlds. If those rocks carry dormant microbial life, as some research suggests is physically plausible, then life could propagate across star systems without any civilization's involvement. The directed version simply adds intent to a mechanism that may operate naturally. Whether or not any civilization deliberately seeded the galaxy with life, the question of our own origins may be less settled than biology textbooks suggest. The precise mechanism by which chemistry became biology on Earth remains, as of today, an open scientific question. Crick's hypothesis sits at the edge of that opening. And if we were placed here intentionally, the civilization responsible may have left behind more than merely life. Some researchers have begun asking whether the answer to the Fermi Paradox might require no telescope at all. It might require looking somewhere far closer. In 2001, philosopher Stephen Webb formulated a hypothesis occupying a strange position between the simulation argument and something more specific, and in some respects more disturbing. He called it the planetarium hypothesis. The idea is not that we inhabit a fully simulated universe. It is that the cosmos visible to us has been deliberately constructed to appear empty, a kind of cosmic theater designed to isolate us from the reality of what the universe actually contains. The premise begins with a direct observation. Every piece of information we possess about the universe beyond our solar system arrives via electromagnetic radiation. Light, radio waves, X-rays, gravitational waves. Every distant star, galaxy, and cosmic structure we have mapped is known to us, exclusively through signals that have traveled to our instruments. We have never directly visited anything beyond our immediate cosmic neighborhood. Our entire picture of the universe is constructed from what reaches us here. This creates a vulnerability. A sufficiently advanced civilization wishing to construct a false picture of an empty universe would not need to alter the actual universe. It would need only to manage the signals reaching our solar system. If such a civilization could intercept or overlay the electromagnetic information arriving at Earth, substituting the signatures of inhabited worlds and alien megastructures with empty static or naturally appearing noise, we would have no means of knowing. The planetarium hypothesis is, in one reading, a sophisticated extension of the zoo hypothesis. Under the zoo model, civilizations simply remain quiet. Under the planetarium model, they actively maintain the illusion of emptiness, controlling what we perceive so completely that our most powerful telescopes find nothing because they have been engineered from the outside to find nothing. This hypothesis is not testable with any current instrument. That represents its most significant scientific limitation. An illusion designed by a sufficiently advanced civilization to be undetectable would by definition remain undetectable to us. Every observation we make could fall within the managed domain. Every anomaly we attribute to natural causes could be a seam in the construction. This places the planetarium hypothesis less in the category of scientific proposition than at the boundary of scientific epistemology. It marks the edge of what we can know from inside the system we are attempting to analyze. If the inputs to our analysis are controlled, our outputs carry no meaning. This is a genuinely uncomfortable position for science to occupy. What the hypothesis shares with other advanced civilization resolutions to Fermi is the implication that the silence is intentional, not a product of rarity or destruction or distance, but of management. The universe appears empty because something wants it to appear empty. Whether that something is benevolent, curious, cautious, or indifferent to our perception of reality is a question the hypothesis provides no framework for addressing. There is a different version of this idea requiring no active deception. It requires only that the observable universe, the portion accessible to our instruments given the speed of light and the age of the cosmos, is simply too small a sample to contain evidence of intelligence that exists beyond it. The universe may be vastly larger than what we can observe. Other civilizations may exist at distances so extreme that their light has not had time to reach us since they formed. The silence of our observable bubble is not the silence of the universe. it is the silence of our corner of it. Either way, we are operating with incomplete information. And the most haunting question may be whether that incompleteness is accidental or arranged. What follows is not philosophy, it is biology, and it may contain the most personal version of the Fermi answer yet. For decades, the search for life beyond Earth operated almost entirely in the realm of theory. Researchers constructed models, ran simulations, and debated probabilities, while the actual observational data remained frustratingly sparse. That situation has begun to change, and the shift is significant enough that some researchers describe this decade as the beginning of a genuinely new era in astrobiology. The James Webb Space Telescope, launched in late 2021 and fully operational by 2022, has granted astronomers the ability to analyze the atmospheric composition of exoplanets with a precision previously impossible. When a planet transits its star, a minute fraction of starlight filters through the planet's atmosphere before reaching our instruments. Different molecules absorb different wavelengths of light in characteristic patterns. By analyzing which wavelengths are absent from that filtered light, researchers can identify atmospheric compounds from thousands of light years away. In 2023, researchers using James Webb announced the detection of carbon dioxide and sulfur dioxide in the atmosphere of a planet designated K218b, a world approximately 2.5 times Earth's size, orbiting in the habitable zone of a cool star roughly 120 light-years distant. Sulfur dioxide can be produced by photochemical reactions involving biological molecules in ocean water under certain conditions. The research team described this finding as tentative and requiring follow-up confirmation. It was not presented as proof of life. Then, in 2025, the same team published results announcing the apparent detection of dimethyl sulfide in the same planet's atmosphere. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. It has no confirmed abiotic production pathway at the concentrations the data implied. The signal was characterized as exceeding 3 sigma in statistical significance, meaning robust enough to warrant serious attention, but not yet at the 5 sigma threshold typically required for a confirmed discovery in physics and astronomy. The scientific community responded with both genuine excitement and appropriate caution. Several independent researchers raised concerns about the statistical interpretation of the data and the challenges of isolating weak signals from instrument noise at these distances. The detection has not been refuted. It has not been confirmed. It is currently the subject of ongoing analysis and debate, exactly as the scientific process requires. What this represents, regardless of the final verdict on K218b, is a proof of concept. The instruments now exist to detect biologically relevant atmospheric chemistry on distant worlds. Within this decade, with continued James Webb observations and the eventual deployment of next-generation telescopes currently in development, researchers anticipate having analyzed the atmospheres of dozens of habitable zone planets with sufficient precision to begin constructing a statistical picture. If multiple independent worlds display atmospheric signatures inconsistent with purely abiotic chemistry, the case for widespread life becomes very difficult to refute. If every habitable world we examine shows only chemical equilibrium and no biological perturbation, the case for the rare Earth hypothesis or the Great Filter strengthens considerably. The answer to the Fermi Paradox may, for the first time in history, lie within the reach of instruments we have already built. But if we do find evidence of life elsewhere, A different and deeply human problem immediately arises, one that researchers are already debating with unusual intensity. The search for extraterrestrial intelligence has been, by historical design, passive. We listen, we scan, we catalog anomalies. We have not, as a civilization, arrived at any systematic decision to actively and powerfully broadcast our existence to the cosmos. That is beginning to change, and the scientific community is sharply divided about whether that change is wise. METI stands for Messaging Extraterrestrial Intelligence. Unlike passive listening programs, METI involves deliberately transmitting powerful, targeted signals toward specific stellar systems in the hope of initiating contact. The logic is direct. If every civilization waits for another to transmit first, contact never happens. Someone has to go first. The counter-argument is equally direct. We do not know who is listening. We do not know their intentions. We do not know their capability relative to ours. Announcing our location and developmental level to an unknown audience carries risks that cannot be quantified, and risks that cannot be quantified cannot be managed. Stephen Hawking publicly stated before his death that attempting to contact extraterrestrial civilizations was, in his assessment, dangerous. He drew his analogy from historical contact between technologically unequal civilizations on Earth, where the outcome for the less advanced was consistently catastrophic. He was not alone. A substantial number of researchers in astrobiology, astrophysics, and existential risk have argued that active messaging should require global consensus before proceeding. Given that any response to a transmitted signal would arrive after a delay of decades to centuries and would affect all of humanity, not merely those who sent the message. Others argue the reverse. If the dark forest scenario holds, we are already detectable. A century of broadcast radio and television signals has produced an expanding bubble of electromagnetic activity already more than 100 light-years in radius. Any civilization within that range already knows we are here. Going quiet now cannot undo that. If we are already visible, the case for maintaining silence carries limited practical weight. The debate also touches on governance questions that science alone cannot resolve. Who holds the authority to speak on behalf of Earth? No international treaty currently governs METI. Individual observatories and private organizations can, in principle, transmit whatever they choose. Several powerful, targeted transmissions have already been sent without global consultation, including a high-powered broadcast toward a star system in 2008. What makes the METI debate more than academic is timing. The development of high-powered phased-array transmitters and advances in targeting precision have made it technically feasible to send signals detectable at stellar distances. The capability exists. The will exists in at least some quarters. What does not exist is consensus, protocol, or governance. The question of whether to call out into the dark, knowing nothing about what might respond, or to remain silent in a universe that may already have detected us, is one of the first genuinely civilization-scale decisions humanity faces in the domain of space. It may be the most consequential decision we make this century, with consequences that neither we nor our grandchildren will live to see fully resolved. But the most unsettling suggestion about the Fermi Paradox may not involve anything we transmit outward. It may involve something that has been with us since the very beginning. There is a version of the Fermi answer requiring no telescope, no signal, and no distant world. It requires only a careful examination of ourselves, our DNA, our biochemistry, and the specific molecular record inscribed in every cell of every organism on Earth. The idea begins with a genuine scientific puzzle. The genetic code is universal. Every known form of life on Earth, every bacterium, every plant, every animal, employs the same fundamental coding system to translate DNA into proteins. The code maps specific chemical triplets onto specific amino acids, and this mapping is essentially identical across all life. This universality is explained by common ancestry, all life descending from a single original population, which is the scientific consensus. But some researchers have posed a harder question. Why this particular code? Of the vast number of possible mappings between triplets and amino acids, the specific code used by all life on Earth appears to be highly optimized. Studies have shown it is extraordinarily resistant to mutation errors, such that single mistakes in the code produce minimal changes in protein function compared to most randomly generated alternative codes. The probability of arriving at a code this optimized through purely random initial assignment is, by some mathematical analyses, extremely small. This may mean the code was selected through early evolutionary pressure on primordial Earth, before the last universal common ancestor, in a period for which we have almost no direct fossil evidence. That is the standard scientific position. It might also, in a more speculative framing, mean the code was designed. Physicist Paul Davies has written about what he describes as the possibility of a cosmic legacy. The idea that a sufficiently advanced civilization might encode information within the genome of a biological organism seeded across the galaxy, not as communication in any conventional sense, but as an archive. DNA is extraordinarily information-dense and extraordinarily stable under the right conditions. A message encoded within the non-coding regions of DNA, the roughly 98% of the human genome that does not directly code for proteins, could theoretically persist for billions of years. This idea has progressed from pure speculation into, at minimum, scientific curiosity. Researchers have begun systematically analyzing genomic data for mathematical structures or information patterns inconsistent with purely evolutionary origin. No confirmed result has emerged, but the methodology is new and the analysis continues. There is also a simpler biological version of this idea requiring no encoded messages. If life on Earth was seeded from another world, whether intentionally or through natural interstellar transport, then our biology itself is evidence of life's presence elsewhere. Every cell in your body may carry the chemical signature of an origin that began somewhere other than Earth, not metaphorically, but physically. Whether our biology records our own planet's chemistry or is a message from somewhere farther away, the answer to the Fermi Paradox may have been within us all along. Not in our technology, not in our telescopes, in the molecule that defines every living thing we have ever found. We have been scanning the sky for signals. The deepest signal may be the one we are built from. Every theory we have examined offers a different answer. Some suggest the universe is full of life too simple to transmit. Some suggest civilizations rise and obliterate themselves before reaching out. Some suggest intelligence is so uncommon that we may be the only minds ever formed in this corner of reality. Some suggest the silence is managed or temporal, or a consequence of our own limited perception. We do not know which is true. That uncertainty is not a failure of science. It is the honest frontier of what any civilization can know at our current stage. But suppose we sit with the most austere possibility, that the silence is real and permanent, that there are no other technological civilizations in this galaxy, that none have dispatched probes or signals or artifacts we can detect, and that the reason is some combination of everything we have examined. Life is rare, complexity is rarer, intelligence is rarer still, and the civilizations that do emerge tend to be brief, separated by unbridgeable distances in space and time. If that is true, what does it mean? First, it transforms our sense of responsibility. If we are the only minds in this galaxy capable of asking these questions, of directing our instruments at the cosmos and comprehending what they reveal, then our survival is not merely a human concern. It becomes a cosmic imperative. The universe has, in us, produced something capable of observing it, understanding it, and perhaps eventually shaping parts of it. If we destroy ourselves, that capacity vanishes with us. There is no reserve, no second opportunity from a neighboring civilization that might carry what we leave unfinished. Second, it changes the meaning of everything we create. Every increment of knowledge we accumulate, every scientific advance, every cultural achievement exists in a context where it may be the only such thing in the galaxy. Not the finest version of something common, the only version of something rare. That does not diminish our problems or render our conflicts less real, but it adds a dimension to their stakes that the Fermi Paradox makes impossible to ignore. Third, it reframes exploration. If the galaxy is largely empty, the long and demanding project of becoming an interstellar civilization is not the act of joining a populated cosmos. It is the act of beginning to fill an empty one. Every world we eventually reach, every system we study and potentially inhabit, we would arrive at as the first mind ever to encounter it. The gravity and strangeness of that firstness is difficult to hold in the mind all at once. Fourth, and perhaps most urgently for this moment, it gives meaning to the question of whether we survive our own critical phase. The century we are living through is widely recognized by researchers in existential risk as among the most consequential in our species' history. Artificial intelligence, biotechnology, climate disruption, and the geopolitical tensions accompanying rapid technological change are all converging within a window that is, by the standards of cosmic time, almost instantaneously brief. Whether we navigate it matters enormously if we are alone. It matters even more if our survival might one day answer the question for another species millions of years from now, looking at the same sky and wondering whether they are the only ones. We began this journey with a simple question. Where is everyone? We have moved through layer upon layer of possible answers and arrived not at a single clean resolution, but at a portrait of a universe that is, in every direction, asking something in return. Whether life is abundant or rare, whether the filter lies behind us or ahead, whether the silence is natural or engineered, the silence itself carries a message. It tells us that whatever we are, it is not ordinary. Whatever happened here, on this world, in this century, is not incidental, and whatever comes next, we are the ones who determine it. The universe is vast beyond comprehension, ancient beyond imagining, and, for all we can tell, quiet in every direction. But quiet is not the same as empty, and empty is not the same as finished. Every answer we have examined opens onto more questions. Every theory we have followed leads back to the same threshold, this civilization, this century, this choice. The silence does not resolve itself. It waits for us to resolve it, and perhaps that has always been the point.